In the 20th century, it was found that certain physical phenomena at the atomic and subatomic scale could not be explained using classical physics. A new theory had to be developed to explain what was being observed experimentally, which led to the development of quantum theory and quantum mechanics. Quantum computing has arisen from quantum mechanics as a type of computing which uses quantum mechanical concepts such as superposition and entanglement to perform calculations with quantum bits called qubits. Using these concepts gives quantum computing a computational advantage over classical computers. This presentation will give an overview of quantum computing and the mathematical concepts behind it, and then we'll explain how those concepts are used in various applications, including neural networks and cryptography. This is just an overview of what I'll be talking about today. So a classical computing bit can only be in a discrete state, 0 or 1, but quantum computing bits, which are called qubits, also have states. However, they are not 0 or 1. A qubit is a two-state quantum system, and qubits can be in a superposition or a state other than 0 or 1. A superposition of quantum states is a linear combination of eigenstates represented as the equation seen on the screen, where alpha and beta are complex numbers, and I'm referring to the 0 and 1 as just 0 and 1 and not ket 0 or 1, just for short. In quantum mechanics, a wave function, phi, assigns a complex number to each point x at the time t. And measurement of a qubit will yield a 0 or 1 because of the collapse of the wave function from a superposition to a single eigenstate. But this is not a direct measurement like it is in the classical computing world. And that's an important distinction because quantum measurement is seen as irreversible. Once you measure it, you destroy the quantum state and replace it with a classical state, and you can't go back to the quantum state once you get that collapse of the wave function. Measuring a qubit can also be seen as a probabilistic determination, which yields a 0 with probability alpha squared or a 1 with probability beta squared. Another way to represent qubits, thinking about the ket notation, is as orthonormal vectors. So 0 is actually a 1, 0 matrix, and 1 is a 0, 1 matrix. Therefore, the superposition can also be represented as the equation seen at the bottom of the screen. An n-qubit system will have 2 to the n possible states. So a 2-qubit system has 2 to the 2 possible states, which is 4, and you can see those states on the screen. So it's evident that as the number of qubits increases, the complexity of a quantum system increases exponentially. The exponential complexity of a quantum system limits the number of qubits that can be used by a quantum computer. Currently, the highest number used successfully is 53 qubits, creating a Hilbert space of dimension 2 to the 53. This was as of April 2021. Another important distinguishing feature of quantum computing is the concept of entanglement. Considering the Bell state seen on the screen, which is just equal probability in measuring a 0, 0 or 1, 1 because alpha and beta both equal 1/2, satisfying the equation alpha squared plus beta squared equals 1. Suppose that the first qubit is measured to be a 1, which implies that the second qubit must be a 1. So here, measurement of the first qubit altered the probability distribution of the second qubit because the state was entangled. Performing operations on an entanglement of states, allowing multiple states to be operated on simultaneously, is taken advantage of in quantum computing, as it is a distinct feature that is impossible in classical computing. And this really increases the speed in which operations can be performed, as demonstrated by Google AI in their publication, Quantum Supremacy Using a Programmable Superconducting Processor. A quantum mechanical system is governed by the Schrodinger equation, where phi represents the state vector of the quantum system, h hat represents the total energy of the system, also known as the Hamiltonian. The quantum systems exist as vectors in a Hilbert space. The time evolution of quantum states can be generated given the state at time equals 0. If the Hamiltonian is not a function of time, then phi of t equals e to the negative I ht over h bar times the system at time 0. So a quantum system of n qubits can be imagined as qubits in, qubits out. Here, the phi in are superpositions of states evolving according to the Schrodinger equation to yield out superpositions phi out, as opposed to a classical system of just bits in, bits out. Instead of just bits, it's the quantum state entering and exiting the system. The output of this system is sensitive to interference from the states. Given a probabilistic outcome, there is interference affecting the probabilities. And controlling this uncertainty is a current area of research in quantum computing. We know that the Schrodinger equation is linear and unitary. It preserves the inner product between the vectors in the Hilbert space. This constrains the quantum system and implies that copying or cloning a quantum state is impossible. So this notion arises naturally from the assumption that exact quantum states are unknown. So if the state is truly unknown, there's no way it could be cloned. So typically when you clone something, you're copying it. So if you have x and you clone it, you get an x squared. But because a quantum state is a linear combination and you clone that, you don't get the same result as you would just cloning an x to x squared. If you clone alpha x and beta y, you don't get an alpha xx and a beta yy. So operations on qubits are performed via quantum logic gates, also known as quantum gates. The most basic operation is the NOT gate, which acts linearly on a single qubit to produce the opposite. So it flips the 0 to the 1, and the beta 1 is flipped to beta 0. And the NOT gate is represented as a 2x2 matrix. And the qubit in vector notation can be represented as alpha beta, therefore the operation is performing the operation on alpha beta will yield beta alpha. And the only constraint on the matrix representing the quantum gate is that the matrix must be unitary, where the matrix times itself equals 1. Quantum parallelism is a feature of quantum computing which allows a function f of x to be evaluated for many different values of x simultaneously by exploiting superpositions of the quantum states. However, you have to remember that the extraction of information about multiple values of f of x is not straightforward. So we have algorithms such as the Deutsch-Jozsa algorithm, which allow us to extract information about quantum gates or using quantum gates such as the Hadamard gate. seen below. So this is the Hadamard gate, 1 over square root of 2 times the 1, 1, 1, negative 1 matrix. This quantum gate acting on 0 produces 0 plus 1 over square root of 2, and acting on 1 produces 0 minus 1 over square root of 2. So it will always produce a result that's exactly halfway between 0 and 1. Now I'm going to go into some of the applications of quantum computing. These include machine learning, using neural networks, and cryptography. As mentioned in the section above, controlling uncertainty in quantum systems is a current area of research. The paper, A Neural Network Approach to Sampling-Based Learning Control for Quantum System with Uncertainty, was provided to me as part of my research on the subject. And in this paper, the authors of the paper sought to find the optimal control for the evolution of a quantum system. And to find the optimal control, deep learning with neural networks was used. In general, deep learning seeks to recover a function based on data using many layers. Neural networks are based on the design of neuronal networks in the human brain. They contain neurons which fire if they pass a threshold value, sending an output number to the next connected neuron in the network. Neural networks are a type of deep learning or machine learning, which use a technique known as supervised learning to train the network. So in supervised learning, a training set is used and the network is trained by feeding in a known input, and to arrive at a result, the network continually adjusts its nodes and weights as it learns. A network is composed of a linear and nonlinear function, where k from 1 to n to the l plus 1 and a here, a is an activation function which introduces nonlinearity to the model. The w, ik to the l are the weights which are multiplied by the input values to produce an output value, and that output value is then sent to the next neuronal layer of the network if it passes a certain threshold value. If the output does not pass the threshold value, then it's not sent to the next neuron in the network. In this case, a neural network approach combined with sampling-based learning was used to achieve a specific target state with uncertain parameters which satisfy known probability distributions. As mentioned above, the Schrodinger equation is used in cases such as this because the transform in a quantum system must be an orthogonal matrix. In this system, U of t is the control which drives the system from its initial to the final state. Two different approaches are used, and I will go over them in more detail, but the two approaches are neural network-based learning control, which I will refer to as NNLC, and finite difference integrated neural network-based learning control, FDI-NNLC. In the NNLC approach, two neural networks are constructed for the quantum system, one for the solution and one for the control. In training the neural network with NNLC, the uncertainty parameter theta is included in the design of the loss function. So we have two neural networks in the NNLC learning control. For the FDI-NNLC approach, only one neural network is used to learn the control function, UT, while the solution of the differential equation phi is solved by a finite difference scheme such as Euler's method, seen on the screen. And note that theta appears in the finite difference scheme here, while above theta was included in the design of the loss function in the NNLC approach. In the training phase, the neural network was trained using fixed training steps with one sample set of uncertainty parameters generated from the given distribution. Then the neural network was tested for the control by evaluating its average performance on additional sample sets of parameters. Euler's method was used in learning the control, so the Runge-Kutta method was used in testing because it has a higher convergence rate. One approach was to sample n sets of parameters, theta, and find the optimized control u of t to maximize mean fidelity. The neural networks here were trained for a fixed number of steps for each sample of theta. In the NNLC approach, we used 10 fully connected feed-forward neural networks. A feed-forward neural network is one that proceeds in one direction without backpropagation. Here, the network proceeded from an input node with a single input T through 5 hidden layers, each with 20 neurons each, and into an output layer. 6 networks were used to learn the real and imaginary parts of the states, alpha 1, alpha 2, and alpha 3. And then 4 neural networks were used to learn the controls, U1, U2, U3, and U4. We can compare this approach with the finite difference approach, in which only 4 feed-forward neural networks were used to learn the controls. And the alphas 1, alpha 2, and alpha 3 were calculated not with the neural network this time, but with the forward Euler method. The key difference in this approach was that the differential equation was solved first before going to the neural network. Instead of using the neural network to solve the differential equation, it was solved using the Euler method. The benefit of using a neural network in this case was that it allowed the controls to be learned without the need to manually calculate the gradients. The NNLC approach also solved the differential equation using deep learning, which avoided the need to actually solve the Schrodinger equation altogether. However, the process of training the neural network was time-consuming and computationally demanding compared to traditional numerical methods, such as just using an Euler method to solve the differential equation. I'm going to go over some of the results I obtained from running the project code which was provided to me. In comparing the NNLC results with the FDI NNLC for 40,000 iterations, the FDI NNLC approach overall seems to be the more accurate approach. However, it was more time-consuming. Both approaches reached a similar average fidelity for 40,000 iterations with a time step of 1/40, but the finite difference approach was slightly better. Using the finite difference approach reduced the error as the time step decreased, while the NNLC approach does not reduce, the error does not significantly reduce with a reduction of time step. Both methods were time intensive on my personal laptop. The NNLC approach with uncertainty of 0.1 and time step 1/60 took 53,497 seconds to run. And for the FDI and NLC approach, the deterministic case with 0 uncertainty and a time step of 1/80 took about 59,000 seconds to run. For this case, I also have the number of iterations to speed it up and ran the code again. And I got an average fidelity of 0.99996024 in 30,068 seconds, which is still higher than what was achieved with twice the number of iterations using NNLC. So I got a very high average fidelity with half the number of iterations for FDI and NNLC compared with NNLC. I'm going to switch over now to some of the applications in the field of cryptography. Quantum computing has many applications in cryptography because of its ability to speed up certain algorithms and perform searches. Many classical crypto systems rely on the fact that factoring is hard, especially when the numbers to be factored are very large. We have crypto systems such as the discrete log and the RSA, which rely on this fact that factoring is very hard. The discrete log problem is as follows on the screen. Given a prime number p and non-zero integers alpha and beta, can we find a positive integer x such that beta is equivalent to alpha squared mod p? If p is a large prime number, for example, 200 digits or longer, there are too many possible choices of x to be computationally feasible for a classical computer to break this encryption. The RSA crypto system uses an encryption key or public key n, which is the product of two large secret prime numbers. If one can quickly factor in, RSA can be broken. And the current security of RSA comes from the large amount of time it would take to factor in. So we have an algorithm, a quantum algorithm called Shor's algorithm, which can factor integers in polynomial time, suggesting that it could break RSA encryption. There is another algorithm called Grover's algorithm, which is a quantum search algorithm requiring big O square root of n operations. A hash function is a function which takes data of an arbitrary length and outputs a hash value of a fixed length. So the secure hash algorithm 256, also known as SHA 256, is a hash commonly used and is viewed as secure by the US government. So it takes in an arbitrary data and outputs a 250-bit string, which is the hash. This is known as a one-way function, which means it's very easy to generate the hash from an input, but it's almost impossible to, given a hash, find the input that the hash was created from. Hash functions appear secure against Shor's algorithm. So it's even secure against the quantum algorithm, but Grover's quantum search algorithm, with its quadratic speedup, could force key sizes larger than 256 to ensure security against quantum algorithms. Grover's search algorithm has also been used to find the optimal weights for a neural network that can then be used in cryptography. And during the training of this network, the weights calculated correspond to secret keys used for encryption. And then generating multiple keys in this way makes it difficult for adversaries to obtain all of the keys needed to break encryption, which is an interesting application using the quantum search with a neural network to increase security. Back to factoring again, classical computers can only get the prime factorization of an n-bit integer through this time here on the screen using something called a field sieve, which is the most efficient classical algorithm for factoring large numbers. The field sieve is exponential in the size of the number being factored. And quantum algorithms can accomplish the same task exponentially faster in n squared log n times log n time. The key requirement for this quantum factoring and other quantum algorithms also is the quantum Fourier transform, which the quantum Fourier transform enables something called phase estimation, which is the approximation of eigenvalues of a unitary operator under certain circumstances. So we have the discrete Fourier transform here on the screen, yk, and then I have the quantum Fourier transform below. And as you can see, it's almost identical in the setup of the equation. But the discrete Fourier transform takes a vector of complex numbers as input, where a fixed n is the length of the vector, and it outputs the transform data y0 to yn minus 1, which is yk. And then the quantum Fourier transform below is equivalent to the equation on the bottom of the screen, where the amplitudes yk are the discrete Fourier transform of xj. This transform is a unitary transformation, which means it can be used in quantum computation in algorithms like Shor's algorithm. Phase estimation is used in solving the discrete log problem and in order finding, which leads to factorization. Additionally, we have something called the no cloning theorem, which was mentioned at the beginning of the presentation. And this theorem has important implications in quantum cryptography because the theorem proves that a quantum state is impossible to copy, therefore implying that a quantum cryptography key is also impossible to copy, which would offer protection against eavesdroppers and malicious attacks. While quantum computing has the potential to change the field of cryptography by making many classical crypto systems vulnerable to attack, we have not reached this point yet because the high computational volume needed to run algorithms such as Grover's and Shor's algorithm is not yet a possibility, but I think it will be in the future as the potential of quantum computing is expanded to more complex systems with more qubits. In conclusion, quantum computing is becoming increasingly relevant as industries are exploring its potential for solving real-world applications. Applying quantum mechanical concepts can give computers a beneficial advantage over classical systems in certain situations, especially where fast computation is needed, as in cryptography. Deep learning with neural networks is another expanding field with many applications, especially in research and industry. And neural networks can achieve a high accuracy with a relatively simple design. However, the computational cost of both quantum computing and neural networks should be considered, as quantum computers have a large computational power requirements, and training a neural network can be time-consuming and computationally demanding. The end.